As our fourth and final basic law, we apply the Reynolds transport theorem to the first law of thermodynamics. The dummy variable beta become energy E. So let me write again the Reynolds transport theorem. Beta rho d v plus beta rho v r dot n d I dA. In this case, the energy, the dummy product B equals to E, and we can calculate beta, the intensity of the dummy product, and we can show the beta as E. Which is energy per mass of the fluid. We can now calculate the relation of the we can now obtain the relation for Reynolds transport theory related to the energy dE on dt. B is E in this formulation. We now wrap the energy equation for a system dE on dt equals to minus dW on dt, which is equals to d on dt. You should write too much the Reynolds average, Reynolds transport theorem to keep it to your mind. dA. Recall that positive Q denotes that Q positive denote that added to the heat added to the system. And positive W denotes work done by the system. So any work on system is a negative sign. The system energy per unit mass may be several types. So the total E of the system E equals to E inertial plus E kinetic plus E potential plus E order, where E order could encompass a chemical reaction, nuclear reaction, and electrostatic or magnetic field effect. For example, chemical, nuclear, electromagnetic. We can neglect this type of energy in this chapter and consider only the first three terms as discussed before. We had E equals to E inertial plus E kinetic plus E potential, which can be internal. Let me correction here. E internal which shown with U plus kinetic from the previous and the potential energy. The heat and work term could be examined in detail. If this were a heat transfer book, for example, dQ on dt would be broken down into conduction, convection, and radiation effects, and whole chapter written as each. Here we leave the term untouched and consider it only occasionally, using for convenience the over dot to denote the time derivation. We divide the work term into three parts. We have three parts for work term. W equals to W shaft and pressure, and also a work viscous stresses. Three types of work in the control volume that we shown in this chapter with the work done by shaft, work done by pressure, and work done by viscous stress. W.S, W.P, W.P. The work of gravitational forces has already been included as potential energy in this equation. Other types of work, such as those due to electromagnetic forces, are included here. The shaft work is related to the portion of the work that is deliberately done by a machine protruding through the control surface into the control volume. No further specification other than W.S is desired at this point, but calculation of the work done by the turbo machines will be performed in later chapter, for example in chapter 1. So in this chapter we only use work with W.S, for example, for shaft for the moving part, and in this chapter we only use shaft work for the moving part in the problem. The rate of work W.P done by the pressure force occurred at the surface only. All work on internal portion of the material in the control volume is by equal and opposite forces and is self-cancelling. The pressure work equals to the pressure force on a small surface element dA times the pressure work by V that we shown with P on an element can be calculated as Fp, which is equal to also to F equals to minus P minus V dot N dA. So we know we can calculate W dot P work by pressure equals to P V dot N dA. A cautionary remark: if part of the control surface is the surface of a machine part, we prefer to delegate that portion of the pressure to the shaft work term Ws not to Wp, which is primarily meant to isolate the fluid flow pressure work term. Finally, the shear work due to the viscous stress occurs at the control surface and consists of the product of each viscous stresses and the respective velocity component. And we can write for viscous work on the system viscous stresses. Work done by an element equals to minus tau v dA. So viscous law equation where tau is the stress vector on the elemental surface dA. This term may vanish or be negligible according to the particular type of surface at that part of the control value. Solid surface. Let me write on the next page for the viscous work. We had integration of tau v dA, where tau is the stress vector on the elemental surface. This term may vanish or be negligible according to the particular type of surface at that part of the control value. At the solid surface, we have solid surface. For all parts of the control surface that are solid, confinite wall, V equals to 0 for all type of control surface. That are solid. V equals to 0 from the viscous non-slip condition, hence the W.V at solid for surface E equals to 0. Surface of a machine, surface of a machine. Here the viscous work is contributed by the machine, and so we observe this work in the term as the W.S. In this case, the work is contributed by the machine and so we observe this work at W.S. Consider this type of work on W.S an inlet and outlet case, and let me for inlet and outlet problems, at an inlet or outlet, the flow is approximately normal to the element dA. So flow normal to the element dA. Hence, the only viscous work term comes from the normal stress T and NV and dA. So the flow is approximately normal to the element. Hence, the only viscous work term comes from the normal stress with integration on this part. Since viscous normal stresses are extremely small in all part rate cases, such as the interior of a shockwave, it is customary to neglect viscous work at inlet and outlet to the control volume. So you can write the term TMN, for example, is very small. We can write the, for example, 1 W dot P in this case equals to 0, the case 4. So for inlet and outlet flow, we don't have any viscous flow streamline surface. If the control surface is a streamline, such as the upper curve in the boundary layer analysis, the viscous work term must be evaluated and retained if shear stresses are significant along this line. In the particular case, the streamline is outside the boundary layer and the viscous work is negligible. So let me write if the control surface is a streamline, such as the upper curve in the boundary layer analysis. If the control surface is a streamline, such as the upper curve in the boundary layer analysis, the viscous work term must be evaluated and retained if shear stresses are significant along this line. In the particular, the streamline is outside the boundary layer and viscous work is negligible. Equals to 0. So we have 4 type of problem in the case of works with the control with the shear stress. As a result, we can write the relation for total work minus TA. This is the total work done by shaft and work by the viscous flow and work done by the pressure. Let me write shaft pressure and the viscous stress. Where the subject SS stands for stream surface. SS So with this derivation, we can now write the relation for Reynolds average transport theorem, which is d on dt equals to on control volume E, which is plus h bar plus h bar plus enthalpy and entropy plus gz rho v dot n dA. This relation comes from this expression. Consider Q dE equals to dt equals Q dot minus W dot Q dot minus W dot S minus W dot P minus W dot V equals to E, which is U, rho v and dA. And we have also this relation for W dot P equals to, from the above, P dot P integration on control system PV dot N dA, this relation. And with the simplification, if we bring the W dot S P on the right hand side, we can add these two expressions because of the same integral forms. So we can write this relation for Q dot minus W dot S minus W dot V on C, control B, I write E, this is E, rho dV plus P on rho and we can write this relation P on rho multiplied to rho. P on rho, rho Vn dA. If we had a summation on these two integrals, these are E plus P on rho, which is H U plus V2 plus GZ plus P on rho, where P on rho equals to H. P on rho plus U equals to H, and this relation can be obtained and we can write in the next page. Again, Q dot Q minus W dot S minus W dot on control value relation for energy for the Reynolds transport theorem. As mentioned, the shear work term W.V is rarely important. In the bidimensional case, dimensional Energy-Flux term. If the control volume has a series of one-dimensional inlet and outlet, the surface integral reduces to a summation of outlet fluxes minus inlet fluxes. This the last part of the energy equation is S in one dimensional equals to sigma H plus out m dot out minus sigma H plus GZ in m dot in. The steady flow energy equation. We had this relation for the energy equation from the Reynolds theorem, transport theorem equation, which is control value R rho dV plus the flux term, which was H plus out minus E. In the case of the steady flow energy, the first term in right hand side is equals to 0, so we can write the energy equation in the steady state condition, which is out in. And we can obtain a relation also from the quantity equation, which is that the m dot 1 equals to m dot 2 equals to m dot. Anyway, we can now write the relation as m dot out and H2 plus Q minus W viscous. We have also end that here, and the Q is the upper case Q. Now we can write at this equation per unit mass, which H bar, for example, in a summation form. In equals to minus Q lowercase W dot S WS plus W viscous, where Q is Q dot M dot and WS W dot S on M dot. W viscous is W dot V on M dot. The heat transfer to the fluid per unit mass. Similarly, we have the relation force for the viscous work and shaft work. This equation is a general form of the steady flow energy equation, which states that the upstream stagnation enthalpy which is H1 plus and H2 downstream differ from the downstream value H2 divided upstream. Stagnation enthalpy. And downstream stagnation enthalpy differ from the value H2 only if there is heat transfer, shaft work, or viscous flow between section 1 and 2. Recall that Q is positive or if heat is added to the control volume, and the shaft work and viscous work are positive if work is done by the fluid on the surrounding. Each term in this equation has the dimension of energy per unit mass. So each term per unit. Our velocity squared, which is a form commonly used in mechanical engineering. If we divide through by G. Each term becomes a length or head, which is a form performed by civil engineers. The traditional symbols for head is H, which we do not wish to confuse with enthalpy. Therefore, we use the internal energy in rewriting the head for the energy relation. So we can write the head form P1 on gamma plus U1 on G plus V12 on 2G plus Z1 equals to P2 on gamma plus U2 on G plus V2 square on 2G plus Z2 and the other minus HQ plus HS plus H from viscous. So we can write again the form head of energy equation. Internal energy on G plus velocity square on 2G plus Z1 elevation, P2 on the specific weight plus internal energy on the gravitational acceleration, velocity on 2G plus Z2 minus HQ plus HS plus HV. This is the head form of energy equation. In this equation, HQ is Q on G, HS is Q on WS on G, and H viscous is W viscous on G. Are the head form of the heat added, shaft work down, and viscous work down respectively. The term P on gamma is called pressure head. And the term V2 on 2G is denoted as the velocity head. Friction and shaft work in low speed flow. Friction and shaft work in low speed flow. A common use of the energy relation is friction and shaft work. In low speed flow. A common application of the steady flow energy equation is for low speed flow through a pipe or duct. A pump or turbine may be included in the pipe system. The pipe and machine walls are solid, so the viscous work is zero. The equation of the above can be rewritten as the form P1 on specific weight plus 2G plus Z1 equals to Z2 plus minus Q on G. Every term in this equation is a length or head. So let me write every in this equation is length over head. The terms in parentheses are the upstream and downstream values of the useful available head or total head of the flow. So the terms P1 plus P12 on 2G plus Z1 as H1 and P2 plus P2 as H2 downstream, upstream and downstream. Values of useful or available head. Useful or available head of the flow denoted by H0. The last term on the right hand side is the difference between H01 and H02, which can include the pump head input, turbine and head extraction and friction head loss. Always positive. Thus the incompressible flow with one inlet and one outlet, we can write the for an incompressible flow with one inlet and one outlet is equal to P on gamma plus V2 on 2G plus Z equals downstream term, upstream term, and P on gamma plus Z out downstream plus H friction, H pump and turbine. Most of our internal flow problems will be solved with this equation. The H term are positive, that is the friction loss is always positive in real viscous flow. A pump adds energy and a turbine extracts energy from the flow. If HP or HF, pump and HF friction are included, the pump or turbine must be lie between points, for example 1 and 2, between inlet and outlet. This will be described in the next chapter, chapter 6 and 5 and 6, and also thermodynamics study. The energy equation, also there is a correction for energy equation, which is alpha equals to integration on the surface each section dA, where alpha is applied on the velocity terms, and the relation can be written as P on, for example, rho g gamma plus alpha on 2J P2 plus Z equals to P on gamma on 2GV2 plus Z plus H turbine H pump to the H friction minus H pump. In the turbulent flow, there is also a correction factor, which the relation is due the expression of alpha is related to the degree of turbulence, and we have, for example, for a velocity equation of the turbulence flow, the alpha equals to it also this expression of alpha can be calculated from the various degree of m and applied on the velocity component of the energy relation that's derived from the Reynolds theorem, transport theory. This is the end of chapter 3. There are various problems in the problem solution section in the channel.